Good afternoon. We are going to take notes on 4.7 day 2. We're going to start getting into some points of concurrency. And points of concurrency are places where three constructs in a triangle meet up. And each of them have a different name depending on the type of construction that creates the point of concurrency. So the first special name for a point of concurrency is the circumcenter. The circumcenter of a triangle is the point at which all of the perpendicular bisectors of the sides meet. Now, acute, right, and obtuse triangles have different kinds of circumcenters. In an acute triangle, which is where all the angles are less than 90, you can see that the perpendicular bisectors of the sides meet up inside the triangle. So the circumcenter is inside the triangle. Now, for a right triangle, we're going to draw our own perpendiculars. I've already marked the midpoints for you to make it a little easier. So those two sides are the same. Then we're looking for the perpendicular bisector. So there's my perpendicular. We're going to do the same with midpoint 2, which is the midpoint of the sides. And here is your perpendicular bisector. Again, see how those cross each other? And then the last one is the perpendicular bisector of the hypotenuse. And what you'll see is that it meets up with the other two at its base. So this is your point of concurrency. This is your circumcenter. So in a right triangle, the circumcenter is on the hypotenuse. The three lines meet up on the hypotenuse, not inside the triangle like it did for the acute. Okay, the third type of triangle we're going to look at is obtuse. And I've already drawn the perpendiculars in. They are perpendicular bisectors, so those two segments are the same. These two segments are the same. And this is your hypotenuse here. So let's label that hypotenuse. And these two pieces are the same. And all three of the perpendicular bisectors meet up outside of the hypotenuse, outside the triangle. So in an obtuse triangle, the circumcenter is outside the hypotenuse. So it's not on the triangle or in the triangle, it is outside in the direction of the hypotenuse. So three different types of circumcenters, all three of which were created from three perpendicular bisectors. Okay, so now we're going to do a theorem related to that. If a triangle has a circumcenter, which of course is where all three perpendicular bisectors meet up, then the circumcenter is equidistant from the three vertices. Okay, so we're going to do an if and a then. So here's our if. If we have a circumcenter. So again, I've made this a little easy for you. I've marked the midpoints. So those two pieces are the same. I want you to draw the perpendicular. And as you can see, I also kind of put the point there for you so you know where about it should hit. We're going to draw all three of your perpendicular bisectors. And they meet up in the circumcenter. And we're going to name that circumcenter G. So if G is the circumcenter, if G is the circumcenter, then, and this is where it gets tricky. This is still G, so we're going to label it G. The theorem says if G is the circumcenter, then it is equidistant to the vertices. So if I draw a line from G to A, and G to C, and G to B, those three distances are the same. So G to A, the length of GA is equal to the length of GB, which is equal to the length of GC. I think the trickiest part about this theorem is just remembering that the perpendicular bisectors create the circumcenter, but the length of the perpendicular bisector pieces are not the same. You can see you've got kind of a short, a medium, and a long piece. So the perpendicular bisectors make the circumcenter, but the distance from the circumcenter to the vertices are all the same. So it's a very interesting theorem to deal with. Okay, go ahead and turn the page. That was circumcenter. Now we're going to do the incenter of a triangle. Okay, first thing we need is the definition of an incenter. The incenter of a triangle is the point at which the three angle bisectors meet. So in an acute triangle, I've already drawn the angle bisectors here. Let's mark these congruent. So it bisected that one, it bisected that angle, and it bisected the bottom one, and it made I. And I is the incenter. Now on a right triangle, we're going to construct part of this. I've already done one angle bisector for you, so I've drawn the X here. You can draw the angle bisector that goes this direction, and then use this other X out here to draw the third angle bisector. And there is the incenter. Again, angle bisector means these two angles are the same, these two angles are the same, and these two angles are the same. It's inside the triangle. Label it I. Incenter is inside. Okay, now obtuse. On the obtuse triangle, I've done one of them for you. I've given you measuring arcs. Let's do the top one. So we need to have an X to bisect the angle. So I'm going to adjust my stylus, put the stylus on where the measuring arc hits the sides, make an arc, lift the stylus, put it on the other side of where the measuring arc hits the triangle, make an X, draw a line from your vertex through the center of your X. And that should bisect the angle for you. All right, let's do the third one, this one. So sometimes it's easier if you put it outside the triangle. I'm going to put my stylus on the measuring arc, make an arc out there, lift the stylus, put it on the other side of the measuring arc, make another. And so you can see if you're so far out, your X kind of gets flat and hard to use. So that might have been a little farther out, but I can already see where the first two meet up. So I'm going to draw it right there, even though my X was a bit over. So this angle and this angle are the same, and what do you know? The incenter is still inside the triangle. So make a little note here out on the side. The incenter is always inside the triangle. The circumcenter was not. It was in, on, and out. The incenter is always on the inside of the triangle, whether it's acute, right, or obtuse. Okay, let's get to a theorem. Here we go. If a triangle has an incenter, then the incenter is equidistant from the three sides. Okay, so if you have an incenter. So I've drawn it here again to save you a little bit of time. So if you have an incenter, that means that all of the angle bisectors met up here. So we're going to draw in our angle bisectors and mark them as angle bisectors using the incenter that I gave you as a guide. So we have equal pieces there, equal pieces there, equal pieces there. That's an incenter. So given an incenter, then There's our incenter I. If we draw the distance from the incenter to the side, so remember, distance is always perpendicular. So if I draw a perpendicular distance to each of the three sides, you can see that each of those distances are the same. So this one, and this one are all the same. So angle bisectors create an incenter, but the incenter is equidistant to the sides. And of course, we mean perpendicular distance. As you'll notice here, the distance from the angle to the incenter is different. I to C is really long, B to I is medium, and I to A is small. So the constructions that create the incenter are not equidistant. It's the distance to the sides that are equidistant. Interesting theorem. Okay, Roman numeral 3, Pythagorean Theorem. Hopefully this one is a review. So given a right triangle, the sum of the squares of the legs is equal to the square of the hypotenuse. So in this triangle, you have your right angle. The sides next to the right angle are the legs. They can be different lengths. The side opposite the 90 degrees is always the longest, and we always call that the hypotenuse. And according to this, the sum of the squares of the legs, so a squared plus b squared, is equal to the square of the hypotenuse, so it equals c squared. All right, flip the page. We're going to do a little practice. Here we go. Tell whether the information in the diagram allows you to conclude that P is on the perpendicular bisector of AB. And it says tell. Tell means explain. It's another way to say explain. So we can see here's P. Its distance to A and B are the same. And we have a theorem that says if P is equidistant to the endpoints, then it is automatically on the perpendicular bisector. So our answer is yes. And our explanation is if a point is equidistant to the endpoints, then it is on the perpendicular bisector. I'll say it again. If a point is equidistant from the two endpoints, then it is on the perpendicular bisector. Okay, let's look at the next one. All right. Tell whether the diagram allows you to conclude that P is on the perpendicular bisector of AB. All right, so first let's look what they've given us. C is equidistant to A, B, and C. If a point is equidistant to the vertices, it's a circumcenter. Okay, if it's a circumcenter, it's on the perpendicular bisector. So is P on the perpendicular bisector? The answer is yes. And there's two parts to this explanation. C is equidistant to the vertices, so it is the circumcenter. That's the first part. C is equidistant to the vertices, so it is the circumcenter. Okay, now that we've established it's a circumcenter, we can use the theorem, which is the circumcenter is on the perpendicular bisectors of the sides. So if I draw a line through C, what I can tell is that P and C line up. They're on the same exact line. So the circumcenter is on the perpendicular bisector because it bisects those sides. So PC, we'll make it a line. So line PC is on the perpendicular bisector. So see how you had to kind of construct the perpendicular bisector to make sense of it? You're going to be doing that a lot on your homework, is adding construction lines that are not there in the diagram but are true nonetheless. All right, part B, here we go. Use the diagram. It says AE is the perpendicular bisector of DB. Okay, so let's mark that. Perpendicular, and it's a bisector, so these two are the same. And DC is congruent to BC. Okay, so D to C is this long side, and B to C is this long side, and those are the same. All right, so your first mission is to find AB. Okay, so we have a theorem that says if A is on the perpendicular bisector, then it is equidistant to the endpoints. So AD and AB are equal to each other, so I can write an equation, 2x minus 4 is equal to x plus 9. There's our equation. Okay, we're going to solve for x, so I'm going to subtract x to the left, add 4 to the right. 2x minus 1x is x. 9 plus 4 is 13. Now we're supposed to find AB. So A to B is x plus 9. So it's 13 plus 9, which is 22. There's our first answer. And I'm going to go ahead and label that 22. The nice thing is, since AB and AD are the same, this one's also 22. So the next one says find AD. This is really easy because AD and AB are the same. So AD also equals 22. Okay, find DC. Okay, so in the drawing, they've told us that DC and BC are the same. So we can take this quantity and this one and set them equal to each other. So 6y minus 5 we can set equal to 2y plus 5. There's our equation. Okay, we're going to solve for y. So we're going to subtract 2y over to the left, add 5 over to the right. 6 minus 2 is 4y equals 10. This is going to be a fraction. So if I divide both sides by 4, I get y equals 5/2. Okay, so my mission here is to find DC. So I'm going to come down here and finish my problem. D to C is 6y minus 5. I just found y to be 5/2. So DC equals 5/2 times 6 over 1, or 6 times 5/2, minus 5. 2 goes in, 6, you can do this two different ways. 6 times 5 is 30. On the bottom, 2 times 1 is 2. And 2 goes into 30 15 times. Subtract 5, and DC equals 10. So your answer for C is 10. Okay, find BC. Well, they've told us that DC and BC are the same length, so I can say that BC equals 10 because I already know what the other one is. All right, last one, we're supposed to find D to E. So D to E is this piece right here. It's represented by the expression 3x minus 2y minus 5. Well, I've already figured out x up here is 13. and I figured out that y is 5/2. So really, I just need to substitute those in. So dE equals 3 times x, which is 13, minus 2 times y, which is 5/2, minus 5. That's my equation. All right, 3 times 13 is 39. Here the 2's cancel, so I have negative 5 minus 5. So 39 minus 10 is 29. dE is 29. So sometimes on these drawings, you always want to read the directions and mark what they tell you on the drawing. So if it's the perpendicular bisector, mark it as perpendicular, mark the bisection. When these two sides are congruent, mark them as the same, because your answers to the beginning questions will oftentimes help you on the questions afterwards. Also, keep your work tidy. Be sure and box your equation, which in this case would be that one, and then circle your answer so you get credit. Your homework has problems almost identical to this. Make the drawings on your homework bigger so that you can actually label the pieces and parts. All right, that's everything. Have a wonderful afternoon.